Hello, and welcome to this explainer. Look, we are witnessing some absolutely massive, fundamental shifts happening across the entire AI stack right now. We aren't just talking about another new model drop. We are talking about a complete, top-to-bottom architectural rethink. Literally everything from the physical interconnects down at the hardware layer, all the way up to the stochastic gradient optimization dictating your weight updates. It's wild. So today, we're going to decode the latest insights from AI news and break down exactly what these developments actually mean for your day-to-day engineering choices. Here is our agenda for today. First, Cerebrus's non-standard architecture. Second, the inference economics shift. Third, multi-surface coding agents. Fourth, rethinking search and evals. And finally, number 5, the new optimizer era. All right, let's jump right into section 1. Cerebrus's non-standard architecture, rethinking silicon. Okay, so Cerebrus just pulled off a massive $60 billion IPO, closing their first day at $280 a share. This comes on the heels of a deeply significant $10 to $20 billion stake from OpenAI and a 750 megawatt partnership. I mean, that is a scale that completely shatters traditional data center power density constraints. For years, people looked at Cerebrus as this highly ambitious, maybe even deeply contentious bet. A lot of folks thought their path was frankly commercially dubious, but through sheer persistence, they survived multiple compute cycles. This IPO? It's a huge validation for the big chip believers, and it is fundamentally altering the physical realities of modern AI infra. Take a look at this quote. Cerebrus CFO Bob Komin claims there is literally no limit to the size of models they can serve. He specifically mentioned handling internal OpenAI 5.4 and 5.5 trillion parameter models. Now, for that to be true, their architecture must theoretically overcome the massive KV cache and tensor parallelism bottlenecks that completely choke standard clusters. Sure, claiming no limit is classic executive framing, but as engineers, we know what this implies. It means their serving architecture is fully capable of handling current frontier-scale workloads. We absolutely have to take their architecture seriously as a frontier inference platform now, not just some niche accelerator. So what's actually happening under the hood? Well, instead of networking a bunch of disparate GPUs together, We4Scale hardware keeps the entire model in massive distributed SRAM on a single giant piece of silicon. It's exactly what it sounds like. This fundamentally maximizes on-chip memory bandwidth and entirely bypasses those brutal latency penalties you get with off-chip high-bandwidth memory, or HBM. They are attacking the core scaling problem in a way that is intrinsically different from standard GPU topologies. It's a direct strike at the latency bottlenecks that traditionally plague massive model serving at scale. Think about standard GPUs for a second. When you cross that trillion parameter mark, you hit some really harsh constraints. We're talking brutal time to first token latency trade-offs, severe memory hierarchy bottlenecks, and the physical bandwidth limits of interconnects like NVLink. Cerebrus is essentially arguing that their bespoke architecture inherently bypasses all of these standard limits. But, the real question for the industry right now isn't just whether their silicon is elegant, it's whether it can actually sustain high utilization and software compatibility in a market that is so heavily dominated by incumbent CUDA ecosystems. Which brings us to section 2. The inference economics shift. Compute scarcity. $600 billion. That is $600 billion in hyperscaler capex. It's just a staggering number, right? And it perfectly underscores the intense, high-stakes pressure driving this massive shift toward inference economics. There is a very real gap right now between these massive infrastructure cluster buildouts and the actual AI revenue coming in. And believe me, the market is watching these economics incredibly closely. This financial reality is forcing a ruthless, industry-wide focus on hardware utilization and strict cost discipline. Because of that pressure, the whole AI infra market has violently shifted away from pure training prestige towards strict inference economics. The engineering focus is now ruthlessly centered on optimizing TTFT, time to first token, along with TPOT, time per output token, cost per token, and implementing dynamic routing discipline. Serving giant models? That's just a baseline product requirement now, not a flex. That intense financial pressure is dictating our engineering constraints, which is exactly why an architecture promising superior inference economics and lower marginal costs is suddenly becoming so highly valued. All right, moving up the stack to section 3, multi-surface coding agents, the new UX. We are seeing tools like Codax rapidly break out of the traditional IDE using standard language server protocols and MCPs. The adoption is just incredible, over 4 million weekly active users. But the usage patterns are where the real story is.
People are adopting these mobile-first workflows, where their laptops act almost like thin clients or satellite devices, while persistent background daemon sessions on machines like a Mac Mini handle all the heavy lifting. Deep integrations are standardizing everywhere, with platforms like Ollama and Zed adding local open model paths and native canvases. So the competitive frontier? It's no longer just about having the best underlying foundation model. It's about the harness, the UX, and the depth of the whole system integration.
Let's look at Section 4, Rethinking Search and Evals, Back to Basics. There's this really fascinating technical irony happening in modern search architectures right now. We've spent years building these incredibly complex, dense vector embedding spaces, right? Yet primitive lexical retrieval, literally just grep searches and BM25 algorithms based on standard TF-IDF weighting, are actively matching or even beating semantic retrieval in coding agent environments. Engineers are jokingly calling these the zero-parameter and two-parameter models. But it works. When wrapped in the right agent harness, throwing massive parameters and complex embedding retrieval at a problem simply isn't always the optimal systems architecture for deterministic coding tasks. Sometimes going back to basics is the right move.
And when you evaluate the brutal token economics of complex agent routing, you start to see the massive overhead. Look at this Cloudflare JSON experiment interacting with a GraphQL API. A standard SDK setup requires just one step and 15,000 tokens. But routing that exact same request through a full model context protocol server, it balloons the context window to 4 steps and 158,000 tokens, purely because of schema overhead. That is an 8.4x token cost multiplier. When you're dealing with strict compute scarcity and tight inference economics, an 8.4x penalty for complex agent routing is just absolutely devastating to your operational margins.
And observability is getting tougher too. Because agents operate autonomously over these really long horizons, traditional evaluations like OS World and MLE Bench are really struggling to keep up. The massive risk here is deploying black box genie systems that totally lack persistent memory state or visible reasoning traces. To solve this, you need massive observability pipelines with sub-second median write latency just to ingest continuous telemetry and track the agent's thought processes. Consequently, reliability engineering is experiencing a major philosophy drift. We're pivoting from attempting to completely prevent hallucinations toward a mindset of mean time to recovery is all you need. The goal now is building resilient catastrophe machines, where the inevitable agent failures are instantly patched and recovered from.
Finally, let's hit the top of the stack in Section 5, the new optimizer era, math at the top. For years, the Atom family of optimizers has been the gold standard, but it required intense hyperparameter grid searches. Well, the field is now heavily shifting toward what people are calling slight optimizers, highly efficient stochastic algorithms like Meon and Shampoo. Even crazier, algorithmic wrappers like Soda, when applied to Meon, achieve zero-tuning optimization. This completely eliminates the need for expensive weight decay sweeps by automating the optimization process itself. And it astonishingly claims to beat standard Meon, even when standard Meon has been heavily manually tuned. It's wild. We are literally successfully automating the mathematical optimization of the optimizers. On top of that, we're seeing advanced training modalities emerge, like pedagogical RL. This framework fundamentally decouples learning into two distinct streams. You have slow learning via gradient updates to the model's static weights using reinforcement learning, and fast learning through in-context state updates, often referred to as fast weights. By aggressively penalizing teacher models for non-generalizable logical leaps, they create teachable rollout distributions. It's like teaching a student not to jump to conclusions. This significantly improves data efficiency and adaptability, all while drastically reducing the risk of catastrophic forgetting and frontier models. So what does this all mean for us? From massive SRAM-heavy silicon bypassing NVLink limits, to zero-parameter lexical search primitives, to zero-tuning stochastic optimizers, the stack is fundamentally shifting across literally every layer. As you architect your next system, you really need to ask yourself, can bespoke silicon truly overcome the immense gravity of incumbent CUDA ecosystems? And as your coding agents become increasingly autonomous, are you fully prepared to abandon perfect code verification in favor of mean time to recovery is all you need? Your engineering choices absolutely have to shift with these new realities. Thank you so much for joining me on this explainer.